We'll go ahead and get started here. It is 3:15. So first of all, thank you everybody for coming. I think I met most of you at the Avionics kickoff. And so, yeah, the purpose of this lecture today, it is scheduled for 2 hours. I'm hoping it's definitely going to be less than that. But I do want it to be I'm going to go over a lot of sort of different aspects that we use in electrical design. We're not going to get into making a PCB just today. That'll be next weekend. So you've got a week to figure out basically Ultium Designer, installing it on your computer, getting a license. It should be for all students for free. But yeah, today is really going to be about sort of from the systems level, what components exist, how you connect those components, what things to consider when you are designing circuits. And this will be extremely useful once you get Ultium Designer, because Ultium is really just a tool for you to connect schematics up and place down components. But if you don't have an intuition as to what components you want to connect, it's not going to be nearly as valuable. So get started here. Obviously, yeah, the goal is sort of a top-down understanding. So this right here is a systems level diagram of a board. I highly recommend making something like this anytime you get started on any sort of PCB project that is more than simple. And the sort of level of this is just the individual components that you're going to have connected up. So the STM32 right here, as we'll cover later, is a microcontroller. The power for that, like a little LDO, a linear regulator it's called, battery protection circuitry, resistors, some LEDs. And so it pretty much covers all the components you're going to use. And so I'm hoping that by the end of this lecture, you can look at this diagram and pretty much understand what each of these components do. Not how they work, and that's okay, but what they do and how you could potentially mix them together yourself to make something different. So yeah, we use draw.io on the team. We will get all you added to the Google Drive, maybe after this lecture. You can just give me your emails, like a thread in Slack or something. You can add up to Google Drive, and yeah, draw.io just integrates there nicely. So we'll get started. It's going to be sort of a lot of kind of back and forth, I guess, of different kind of components. I don't want to dive too deep into any one thing. Sort of said most of the stuff already here, so I'm going to skip the slide. Yeah, so we're going to start with the super boring, super basics. I'm not going to dwell on it very long, don't worry. But resistors, inductors, and capacitors. So yeah, as you most likely know from high school, resistors, just voltage drop proportional to voltage equals current times resistance. By the way, I'm going to post these slides afterwards, so take pictures if you want to, but you can also just look at the slides after. But you can limit current based on resistance, and the current limiting feature is especially useful when you want to turn on an LED. LEDs will sort of pull an infinite amount of current if you're not careful, or like as much as they want to. So you need to have a current limiting resistor. They're useful there. They're also useful for, very common in digital electronics, is to pull a pin up or pull a pin down. What that means is you are very weakly causing that pin to go to, say, 3.3 volts to pull it high, or very weakly go to ground to pull it low. What I mean by very weakly is if you have a 10 kilo ohm resistor, and let's just say you have like 3.3 volts, you're going to have less than 1 milliamp of current flowing, so a very small amount. Now, it's enough that when you measure that pin, or like some device measures that pin, it does read as low because it is low, and there's a very small amount of current sort of making sure that it always stays low, no matter what's going on in the rest of the circuit. But as soon as you have an active device getting on that bus, like let's just say your microcontroller, think like Arduino, Raspberry Pi, if it decides to drive that pin high from a state of not doing anything to driving it high, the resistor is not strong enough to stop it from driving it high. So it just sort of keeps it in that state. It'll make more sense as you do PCB design, but pulling up and pulling down is probably the most common use for a resistor in digital electronics. Configuring ICs is also something I'm not going to dive into too much, but when you have very specific specialized integrated circuits, they come from the factory with a lot of different features, a lot of options, and typically the way you set those options is by using different resistors, like 10K for mode 1 and 50K for mode 2. So it's useful for that as well. Resistors generally behave pretty well compared to the theoretical models when you actually go to build them. The tolerance in terms of the actual resistance value is around 1% usually. Bad resistors will be like 5%. Don't buy those. You can get cheap ones that are 1%. If you're looking for really precise, like 0.1%, it does get a bit more expensive. Everything is going to have a temperature effect as well. So if it gets really hot, really cold, the resistance will drift. Usually this isn't an issue when you're using resistors. You don't use them for like ultra precise. You just don't. But it's generally not a problem. Resistors also do act like an inductor a little bit at high frequencies, so you got to be kind of careful with that. That is generally not a huge issue, though. Resistors are pretty well behaved compared to the rest of the passives we're going to look at. Capacitors, I'm sure you are sort of familiar with the concept. It stores energy, and it basically wants to maintain a constant voltage. What this means is that if you've got some sort of alternating signal, the capacitor will try to smooth that out. Its ability to smooth that signal out is proportional to its capacitance value. A small capacitor can try to smooth out the signal, but if it doesn't have enough energy storage capacity, there's just going to be a limit to that. So the key use for capacitors really is for decoupling, which is something we'll cover, and just general energy storage in power converters, we'll cover later as well, buck and boost converters. And also configuring ICs. Sometimes they require a capacitor to set some sort of mode. And analog and radio frequency filters, which we're not going to cover today, but they are used in that. So yeah, decoupling, the concept of decoupling is basically when you have a PCB, you have a lot of different components on there that are pulling power at different times for different reasons. You have, like, let's just say USB as your input power supply from your laptop. Any sort of noise or glitches or just any non-idealities in the power supply, which is always going to be the case. Power supplies generally suck, especially ones you haven't designed yourself. Like external power, like USB power is terrible. And what you want is when your microcontroller needs to do some analog calculation or read something analog, do some digital calculation, it's going to pull power off the digital line. And you want to make sure there is basically a energy storage device close by where it can source that power from quickly. Because if you have a really distorted, noisy supply that's far away through like a USB cable and your microcontroller asks for some current to do a calculation, there's a high chance it will potentially glitch and either not work, corrupt your program, etc. This is really in the worst case. Ultimately, what this comes down to is you put capacitors on all your power pins, just between ground and power. And what this means is that it smooths out the voltage waveform nearby, and you really want these to be as close as possible to the pin physically. We'll cover this more when we get into Ultium in terms of the actual physical layout, but generally capacitors are a very location-dependent thing of how effective they're going to be, especially at small values. So this schematic here is just a part of a microcontroller. The way it's laid out, these are all the power pins, and we can see we've got one capacitor per power pin. At a schematic level, they're not directly visually connected, but because we have labeled them both 3.3 volts, when we get to layout, this will connect up, and this will make more sense when we actually get into to Ultium Designer. Yeah, any questions? Yeah.
Capacitors on the left, the A3, B3.
Yeah, it's a good question. So this is sort of the standard way of making things look in Ultium, and it definitely is. It looks very confusing if you're not into Ultium, but it's just basically saying that. So we have these right over here. These A3v3 is like analog 3v3. We sort of separate analog and digital power again for noise reasons, and so this is the same as the capacitor bank on the top, but we've just put it physically different so it can be visually distinct. And yeah, it does look weird because they're not connected. You're like, why not? But they are. It's just you've labeled them right. My Zoom just stopped responding, so I'm gonna real quick restart that. Yeah, capacitors good for decoupling. Ceramic capacitors are typically used for this. As in this image, you can see the ceramic capacitors are the sort of little brown and gray guys. And then you have your standard, probably what you've usually seen as a capacitor, the electrolytics, these big guys. And so they have different purposes. Generally, we don't use the big electrolytics except for very specific power applications. The ceramics are more than good enough for digital electronics. There is a lot of non-idealities with capacitors. They're probably the worst passive component out there. So you got to be really careful when you're doing designs. The main ones, they're susceptible to DC bias and temperature effects. So what that means is if you have your capacitor around 0 volts, let's just say, and you have a small little AC signal maybe flickering between like 0 and 1 volt, the capacitor will behave to its rated capacitance value. Like let's just say 1 farad. It'll be very good at filtering that out. But the thing is, if you have let's just say 100 volts as your base voltage, and then you have some sort of AC signal flickering around 100 and 101 volts, there's like a DC bias there, right? It's not moving over the full range, but it is sort of offset from 0. And that can make capacitors, they lose capacitance very quickly under that effect. So based on this graph here, this is sort of a rough example where if you have a DC bias of up to even just, let's say, 20 volts in your capacitor, it could be as bad as 90% less than the rated amount. Oh, my Zoom just started up again. Anyway, everyone left already. So there's also temperature effects, which we'll cover on the next slide. But again, if it gets too hot or too cold, the capacitance value can go down like crazy. So when you're designing like power electronics, you get a capacitor. This capacitor is rated for 50 volts. It will not explode if you give it 50 volts, but it will virtually suck. So you have to really consider that. With using like decoupling capacitors on a microcontroller, you have to worry about this quite a bit less because microcontrollers operate around like 3.3 volts. And if the capacitance value is a little bit less, it's kind of fine. But when you get into DC-DC power converters, the actual capacitance value is one, really important for the output stability, but even the controller itself can get confused and make a really unstable output if the capacitance is not what it expects. But I won't dwell on this any further. Another effect is the equivalent series resistance, ESR. Obviously, I told you capacitors want to keep voltage constant if they can, as much as their amount of energy they have left will allow them to do. There's also one additional constraint in terms of the capacitance. There's also the equivalent series resistance. They cannot dump an unlimited amount of current. Even if a capacitor had an unlimited capacitance, there's a limit to how much current they can dump because there's basically a resistor in series with the capacitor, just because of how it's manufactured and real life limits. And what this means is when you look at the actual resistance of a capacitor or the impedance complex, I don't want to maybe dive into impedance because some of you guys might be in EC, may have just started, may have been different years. Actually, show of hands, who's in first year? Okay, good. I'm glad I'm covering this. So you'll probably learn some of this in your classes too. But impedance is like resistance, just more complicated and way more annoying to deal with. But yeah, you'll cover it in class. It's not super critical. Effectively, what this means is that if you have some AC signal, the frequency will very heavily affect how the capacitor acts. And so at a very low frequency, compared to a high frequency, compared to what's called a self-resonant frequency, you get very different behaviors in terms of the resistance of the capacitor. So a very low resistance means the capacitor doesn't have to work, not have to work very hard. It's very capable of filtering fluctuations. What that means is this particular capacitor we're looking at ideally would be used to filter some frequency around 10 megahertz. That would be like phenomenal. It's going to have like amazing resistance. But if you're trying to filter like 10 gigahertz, which is obviously an extreme case, it actually behaves like an inductor. It completely switches and behaves like an inductor at higher frequencies. And really what you're seeing is mostly capacitance, and then they sort of, the inductor starts happening and they're competing for each other. And then you get like a really good resistor, like a small good resistor, and then you start getting more of an inductor. So anyways, what you'll notice is that these effects, funny stuff starts happening again around 1 to 10 megahertz. This is relatively high, but just keep that in mind when you're working with higher frequency stuff. But for power decoupling on a microcontroller, you don't have to worry about this. But power electronics design, like actually converting tens of watts between different voltages, you do really need to consider this. Here's roughly the sort of temperature effects. And so it's not as egregious as the DC offset, which you can get like minus 90% performance. It's not that bad. Even in the worst case, you're only looking at like minus 50%. But this is definitely still something you need to consider. Typically for RF applications and when you're configuring an IC and the exact value of the capacitance is really important over a particular range, you use COG capacitors. Now the problem with that is they don't have very high capacitance or voltage rating values. So, and if you don't have a high voltage rating value, you might find yourself further along that derating curve. And so it's always a trade-off between voltage rating, capacitance, temperature variation. I'm going to be honest, typically temperature variation is not that big of an issue just because like even if you look at this graph within the range of between 0 to 50 Celsius or like 40 Celsius, that's pretty much like our rocket's not going to Antarctica. It's not going to the surface of the sun. So typically it's going to be okay. X7R is the most standard, and you're not going to be able to get the perfect capacitor in a small size. So it's just something to be aware of. When you're doing RF or really sensitive things, you do want to go with the COG type of range. So inductors are pretty straightforward. There's really not much to say. They're the same as the capacitors in the principle they store energy, but rather than wanting to maintain constant voltage, they want to maintain constant current, and they do this proportionally with their inductance value, their ability to store current. Most commonly used for power electronics. This is pretty much all we use them for. There are RF and analog applications of these guys. Schematic you're seeing right here is a bucket converter, which we'll cover later, but is a DC-DC switching converter that converts, this one in particular does 24 volts to 8.4 volts. And you can see the inductor is right here in the middle. It's the sort of key energy storage element. There is not too many on ideologies with them that you'd need to really worry about unless you're making buck converter, which I guess is what you're using for. DC resistance, there's always going to be some resistance just because it's a wire. Saturation current, this one's a little bit more annoying. If you're making a really high power buck converter, like 20, 30 amps, the way that an inductor works is you basically have a ferrous core and you have a bunch of wires wrapped around it. And the energy is stored in the magnetic field that is generated. Now, the thing is, materials are not perfect and they cannot necessarily store an infinite amount of energy in that magnetic field. And if you go past a certain current, the core will what's called saturate, and it will just not behave like you want it to. You will not be able to, it'll behave like a resistor, basically. And then core losses are sort of a more niche thing. But when you switch the magnetic field in a switching converter, the alignment is changing internally of the magnetic dipoles, and that will cause energy losses. But yeah, not that crazy. Any questions about the basic inductors, capacitors, resistors? Cool. Yeah, so there's a few different kind of diodes we use. Obviously, an LED is probably the one you're most familiar with. It is fairly straightforward. It just creates light. But the way that it works electrically is there's a small nuance to it. It's not like a resistor where it like sort of draws some amount of current based on the voltage you put on it. It basically drops a certain amount of voltage across it. And that is a constant amount, which means that if you don't put a current limiting resistor and you just have a great power supply, the LED will just be basically is a short circuit and will draw like an unlimited amount of current. In reality, that will turn into the LED just burning itself out really fast. So you do need to add a current limiting resistor always. Yeah, it's pretty straightforward. There's a little calculation you can do. There's calculators online. Just need to be aware of that. If you provide a voltage lower than 2 volts, it will just not turn on no matter how you do it. 2 volts is just an example for this one LED. Some of them are like 1.5, some of them are 2.2, but be aware of that. 1 milliamp to 30 milliamps is the typical range for these guys. So that's an LED, drops about 2 volts. Power diodes are very useful devices, and they typically, you want them to drop as little voltage as possible. An LED, just sort of, you're trying to get light out of it. A power diode, you're specifically trying to control the flow of electricity. An LED obviously only works if you plug it in the right way. That's sort of just an annoying part of it. For diodes, you're really trying to make the best use of that functionality. There's a few types of diodes used for power. Schottky and Zener are the most common. Schottky is the best in terms of highest efficiency. It'll have the lowest forward voltage drop. Any amount of forward voltage drop is energy lost, which does limit diodes to sort of medium power applications. They are used in non-synchronous switching converters, which we will cover later, but like a buck converter, and then reverse supply protection because the diode only allows flow in one direction, so you can put it in series with your supply, and if you plug it in backwards, the current just won't flow. And you can also use it for power supply redundancy, which is what it's currently used for in this little schematic up here. I basically got some USB power coming in, and then I've got our overall wide system power, and the diode will drop about 0.3 volts. What that means is if you've got, you've got 3.3 here, 3.3 here. The diode at the end here, it's only going to be able to like provide 3 volts. Because diodes only allow current in one way, what this effectively means is that when the 3.3 volt supply for the whole system is usually on, there's no problem. This diode will not conduct any current and it will not turn on. It just chills there. But if the other parts of the system power were shut off, like when you have it on a test bench, it's not hooked up to everything else, this diode would allow current flow because there would be no source here, and you would get about 3 volts here because you would have 3.3 minus 0.3. So you don't have to study this exhaustively, but this is just an example of where a diode is very useful, a power diode specifically. We use these across the flight system. I think there's at least 2 or 3 hanging around. Another nice, kind of more niche, but very important use of diodes is suppressing transient voltages. So our previous diodes, you try to get as low of a voltage drop as possible. Think like 0.7, 0.3 volts, and that's sort of the goal. TVS diode is a little bit different. You're actually looking for it not to conduct any voltage for quite a big range, and that's pretty easy to do. Obviously, it's much harder to make diodes that have a really small voltage drop, but if you just want to like arbitrarily jack it up, you can do that in the manufacturing process. And really the point of this is, let's say you have some pin on your microcontroller that can only handle up to 5 volts. Can only handle up to 5 volts before it breaks. You can put a diode like this on the line. And what that means is that if it goes above 5 volts, now the diode will start conducting and basically just sink that current to ground, which will potentially sacrifice the diode in some different cases. But ultimately what it ends up doing is locking the voltage at 5 volts, because once it reaches 5 volts, it starts just conducting the current down. It's not a perfect protection, but it's very useful in digital electronics that have interfaces to external things. Pretty much it. All right, microcontrollers. This is sort of the meat and potatoes of avionics. We do a lot of microcontrollers. Every single board has a microcontroller on it. They are programmable chips with inputs and outputs. You guys are probably mostly familiar with these guys. You've probably seen them around Arduinos, Raspberry Pis, ESP32s. You program them in C or C++, or Rust if you're feeling adventurous. So yeah, we don't use Arduino or Raspberry Pi. We use STM32, which you may or may not be familiar with. Obviously, we discussed it at the last kickoff, but generally, it's the industry standard for microcontrollers. So like your toaster, smart fridge, all these things use STM32. Even satellites, especially satellites and aerospace, uses STM32. It just kind of becomes such a ubiquitous standard, and the company behind it has a lot of tools for it. There's a lot of options, and they are very high performing. So it's sort of the go-to, and we use that. Obviously, it's a little more complicated to set up and use, but once we do get that setup process done, they offer a ton of advantages that like Arduino just could not possibly compete with. Yeah. So quick side note, microcontrollers need some sort of timer to basically make sure the clock ticks correctly. And the way that is typically done is using a crystal oscillator. So you basically apply some voltage to it, and because of the exact structure of the crystal and the way the device is designed, it will oscillate at a very specific frequency. Internal oscillators are typically okay. Most microcontrollers do have them included. They're around plus or minus 2% at a specific temperature, but as temperature drifts, which it can on hot boards, that does drift out of spec, which is sometimes not an issue, but sometimes it is. Typically, the go-to solution is a temperature-controlled oscillator, a TXCO, which basically, there's multiple approaches to making them from a manufacturing perspective, but they're very resilient to temperature variation and have a very, very good frequency accuracy. So they're good reference. So we use those on most boards. In terms of interfaces, things you can do with microcontrollers, I think the most obvious one you've probably done is like turn an LED on or off, or you've seen that at least. And you can do this with GPIO pins, general purpose input output. They basically, in code, you can set the pin to 0 volts or 3.3 volts and turn things on or off. Pretty basic. These pins depends on what microcontroller you have, how much functionality they have. Typically, what you can expect is that you can source current to bring an LED on, to turn it, bring it high, or you can sync current. This is like maybe less common to look at explicitly, but if you ever have like a controlling some other device or any sort of like MOSFET switching on a motor or something like that, you're going to need an external controller. You probably will be pulling low sometimes. The current capability is very limited, 4 milliamps, max 20, depending on the microcontroller. This means that if you want to control high-power devices like driving a motor, you are always going to need an external switch of some kind. So that is something to consider. It's about enough to turn on an LED. And just a small note here, not all microcontrollers, we've actually had this issue on UTAT, not all microcontrollers can source current, like they can actually generate a positive voltage. You can basically float the pin to whatever you want, like float it to 3.3 volts, and it can pull the pin low, but it cannot pull it high. And just something to consider that, you're not always going to have both functionalities. That's the most basic interface. All pins on a microcontroller are going to have this functionality. But you can't really do a lot with this because most devices you want to communicate with, you're going to be wanting to send a lot of data to, potentially read analog inputs, et cetera, et cetera. So just turning a pin on or off is not going to be enough. So most microcontrollers embed specialty interfaces on specific sets of pins that you can configure to interface with other devices. SPI is an example of this. Serial Peripheral Interface is what it stands for. And basically all it is a method of sending data to and from devices, like from a microcontroller to a sensor, like an accelerometer, gyroscope, temperature sensor, anything like that. I don't want to get bogged down by the exact details of the protocol, but essentially the pins you have is a chip select pin, which says, hey, I want to talk to this device right now. So if you have multiple devices on the same SPI bus, you don't need to have, like, if you have 4 devices, you don't need to have 16 wires. You only need to have your 3 that can be shared across all devices, and then an extra 4 to tell each device, hey, I'm talking to you, talking to you, talking to you, etc. And basically what you do is you have the clock line, you initiate a transaction, like sort of a data transmission, by pulling the chip select line low from the microcontroller. You just pulse the clock line, and as you pulse the clock line, you change the value on the MISO and MOSI lines, which is master out, slave in, master in, slave out, etc. Now, the nice thing is you don't actually need to, you really should understand this protocol, but from a firmware programming perspective, you don't actually need to like worry about bringing the lines high and low. It's just about when in code, you'll call like transmit some byte. You'll know this is what's going on. But realistically, there are libraries that handle the actual bringing high and low at a specific time of the pins. This right here, just screenshot Altium, is the barometer on the FMC. And so you can see there's like power, ground, chip select. And there's 2 chip selects on this pin. On this chip. It's super weird. And then MISO, MOSI, S clock, and that's shared across all the sensors. So this is useful to know. I2C is a very similar, comparable protocol. It's we don't use it as much. I'm not going to go into as much detail. It only requires 2 wires. It's quite a bit slower. I guess I didn't really highlight the advantage of SPI. It can go really fast, 4 to 50 megahertz, which is a very good fraction of the microcontroller's overall processing speed. So it's very competitive on that in that regard. I2C is much slower. Can only it's a 2-wire interface. You don't need a chip select pin. All the devices basically come pre-programmed from the factory with an ID, which is an advantage, but also kind of a disadvantage because it means that if you want 2 of the same device, you basically just can't have it because you have no way of like discerning between them. It's okay. It works. The data line is bidirectional, so you have one clock line and then data can flow both directions in one line. UART is a very, very ubiquitous standard. It is basically just bytes over a wire. Most commonly used to just send text, like you can just send hello world over UART. There's nothing complicated to the protocol. You just pulse the wire up and down, for your bytes. It's typically used between sort of, I would say, more intelligent devices talking to each other, like a microcontroller talking to another microcontroller, or talking to your computer, for example. And so it's pretty straightforward, point to point. That is one of the disadvantages. Is unlike SPI or I2C, you don't have like a bus where you can put like 10 devices on it and you just have 2 pins on your microcontroller. If you want one UART interface going to one other point, like it is point to point, you cannot share devices on the same bus. But it's it's good. It's good. So far we covered interfaces that are sort of on the board, and they are good. They go high and low between 0 and 3.3 volts. And on a PCB, on some short wire harnesses, it's not really an issue. But in the real world, especially in aerospace, where you have rockets that are 100 meters tall, you have spacecraft that are a few meters wide, or you have our rocket, which is a few meters long, you want to transmit signals potentially at high speeds over that range. And it's not obvious just sort of thinking about it, but it just turns out that in reality, when you make really long wires that only go between 0 and 3.3 volts, any sort of interfering radio frequencies, like even from your cell phone, from a walkie-talkie, can easily disturb those signals and cause false ones, false zeros, interrupt your data transmission. And you can also have, if you're transmitting a lot of power or data over those lines, you can cause interference and potentially cause other devices not to work properly. So the solution to this is differential signaling. Differential signaling, I basically just look at the diagrams, but rather than just sending a ground and like a 3.3 volts as like a positive, you have 2 signals that are not, the negative one is not necessarily ground. It is just tightly coupled to the positive one, and you basically send a difference. So you pull the negative side low, pull the positive side high, and then at the output, what you do is you read the difference between those 2. Is sort of shown here. The key advantage is, as is on this lower diagram, if you have some sort of noise that ends up happening because of external interference, it affects both lines equally. And so at the end, when you end up subtracting off the 2 lines, you get a clean signal out. And obviously, from a physical, I think I might skip ahead here just a second. From a physical perspective, the only way this possibly works is if you actually be good and twist your wires and keep them close by. Differential is not magic. It's just a way for you to keep the noise on both of them. And so, PCB layout-wise and wire-wise is the same way in your Ethernet. When you open it up, you see the twisted pairs. It's because Ethernet is a differential signaling protocol, among many things, high speed. So rolling back here, that's differential signaling. Not going to say much more on it there. Let's drive into an actual application of differential signaling. So in our rocket, between the flight management computer, power management board, and all the peripheral boards, we use CAN, Controller Area Network. It's an automotive standard. It's used in some industrial applications. It's actually only 2 wires, which is very convenient. And it is a differential signaling protocol. So you're like a microcontroller can only really generate 0 and 3.3 volts. It can send complex signals with interfaces doing that, but it really cannot generate this sort of differential situation. Like inside a transceiver, you might even have like an actual transformer to do this differential signaling. So it really cannot be done inside a microcontroller. What you need is a dedicated chip, and this will be a common theme for differential signals. So you have your microcontroller provide some data inputs and outputs, and then you just have your this thing embeds like all the drive logic, transformer, etc., and it outputs that. That's pretty much it. So we do use this, and there are hardware considerations with the differential like layout and wiring. Another differential interface we use is RS422/485. They're effectively the same thing, but just different applications. 422 is only point-to-point, so it's like UART, where you have device A, device B, they talk to each other. You can't do much better than that. 485 is a slight variation on the way the electrical stuff is laid out inside the chip, which allows you to have, it's sort of like CAN. You can have multiple devices on the same bus. Same thing, you need a transceiver. Really, all RS422 and 485 are, it's really just a UART over a special electrical signal. But in terms of the inputs and the outputs at both ends, you're only looking at UART signals. You send hello world, you get hello world out. There's no packet structure. Like CAN does have a specific packet structure, which firmware sort of has to worry about. But RS422 is just like electrical method of sending bits. Any questions so far on this? All right. Yeah. So, okay. We'll cover power converters. So, yeah, power converters are very important in electronics. Generally, you will have some sort of input power, and it is extremely unlikely that your input power source will match exactly with every single chip on every single board. You are most likely going to need to generate some intermediate voltages to drive those chips. On the flight system for the rocket, this is most apparent by the fact that we have a battery on board, which not only is like kind of a random voltage, it's a random voltage that changes over time as a battery discharges. It can change up to like 25% throughout its discharge range. And so we need to use converters to regulate that to a constant specific voltage to drive everything else. There's 2 main methods of doing voltage conversion. The first one is using a linear converter. These are sort of the old ones that came out initially like 20, 30 years ago. And basically what they do is they just dissipate any voltage difference as heat. This means they can only bring the voltage down, obviously, and they're very inefficient, but they are also very simple and cheap. So there are some sort of trade-offs as to when you would use them. The gold standard for power conversion, though, is switching converters, which is shown on the bottom here. As you can see, substantially more complex. These both provide the exact same function of reducing the voltage, but the lower one obviously is switching. They are a lot more efficient and can handle much higher powers, which we'll cover briefly. But yeah, LDOs or linear regulators are much lower noise, though, because they're not switching anything, so they're good for RF and analog applications. Quick calculations here. If you're using a linear regulator to convert 5 volts to 3.3 volts at 2 amps, you dissipate about 3.4 watts. I would completely understand if this number means nothing to you. In my personal experience, if I were to dissipate this amount of heat on like a small IC, that IC would probably get at least 150 degrees Celsius hot pretty fast. And 38 watts is like impossible. It's going to explode right away. And so this is like if you're doing 24 to 5 volts, which is a realistic application that we actually do in the flight system. So yeah, not good for that application. But if you do have a low power, low voltage difference, for example, 5 volts to 3.3 volts at 50 milliamps, this is realistic for a small sensor, a small microcontroller, or some RF application. You are only dissipating less than 0.1 of a watt, and so it's pretty reasonable. You just got to make sure to pick the right the right application for that. yeah, quick calculation on the buck converters here. Don't want to dwell on this too much, but they can typically achieve up to 95% efficiency. There's no constraints about the voltage dropping, the current running across it. It's really just the total power and what the efficiency is. And so you can do the same example as before that would have exploded the LDO. Instead of dissipating 38 watts, it dissipates around half a watt. So you can do much better. They are harder to design and more expensive, but definitely worth it. Yeah, so we'll talk about a couple types of DC-DC switching converters. So I just want to say, like, switching converters are an extremely deep topic in terms of getting them right, both from a component selection perspective, configuring the IC, and especially the layout. There's a lot that goes into it. There's a lot of complex effects that can generate heat and cause it to get a lot hotter than you expected. But we'll cover basically what exists and then how the most simple one works. And then if you guys are interested or you end up working on a project within UTAT that involves more advanced version of that, obviously you can look into that at that point yourself. But I just want to say it's definitely a very broad topic. So, as the slide says, buck converters generates lower voltage, boost converter, higher voltage. And then a textbook buck boost, technically, it can generate a higher or lower voltage. Technically, it actually flips the polarity. And so you get a negative voltage on the output, which is like extremely useless in most applications. So what you actually end up doing is what's called a 4-switch buck boost converter, which generates a higher or lower voltage, but with a normal polarity. And that's what you're seeing on this diagram here. So your switches are these MOSFETs, which we'll cover as well. But MOSFETs are just electrical switches that can turn on or off based on another signal. So, yeah, okay. This is kind of dense. Bear with me though. Buck converters operate very similarly to all switching converters. Really, the only difference between buck converter, boost converter is where the switch is and where the switch is. That's pretty much it. You're always going to have an inductor, a capacitor, and some sort of load. You're going to have some sort of rectifying diode. Now, in some applications, you replace this diode with a MOSFET that is actively controlled, higher efficiency, but generally the concept goes like this. You have some sort of input voltage, say it's like 20 volts, and then say you want to generate an output of 10 volts. You take your switch here, you just PWM it, which stands for pulse width modulation, basically just turning it on and off 50% of the time. And then, you sort of think about it, you've got 20 volts half the time, 0 volts the other half of the time. You basically got 10 volts, so you're good. Unfortunately, if you were to do that, you would just get a really spiky output signal. So you need to smooth it out. And the way you smooth it out is using an inductor as a constant current device and a capacitor as a constant voltage device. You put these guys together and you effectively end up getting a smoothed output signal, as you can see on the lower graph here. And you do need a controller to basically change the PWM based on what the current input and outputs are. But that's pretty much it. That's all it is. You turn on the MOSFET, it allows current to flow, and then you turn off the MOSFET, and then current keeps flowing around this loop, and the diode basically allows the current to flow in a loop like this while the switch is still off. But then when the switch turns on, obviously current now can flow back through the supply. But I'm not going to go into too much detail about that. But just know there's a lot of considerations with this. In particular, selecting the MOSFETs, inductor, capacitor, controller. The key factor is the switching frequency. This is how fast you turn it on and off. Sure, you're leaving it on and off 50% of the time. That's already pre-established for our 20 to 10 volt example. But how often you switch it is pretty important. The general rule is that higher switching frequencies allow you to get away with smaller components, but higher switching frequencies also get hotter, less efficient, because every time that you switch a MOSFET, you lose a little bit of energy. Forget anything else going on in the circuit, forget the resistance of the MOSFET, just switching a MOSFET on and off, you lose energy in the form of heat. So it's a consideration. You also have stability margins and stuff, and it's a whole, it's ideally you never have to deal with this, but if you test it and it's not working properly, which I have, you might have to start doing some calculations as to the stability, but usually you don't have to worry about that. So this is a good segue into MOSFETs. They're basically just digital switches that can turn on or off. Do you guys want a break? I'd say there's probably 30 minutes left. Do you guys want to take a little 5-10 minute break right now, or do you want to keep going? Show of hands. Yes, good. Okay. All right. Sweet. Yeah, so there's two types of MOSFETs. There's an N channel, which is the most common, and there's a P channel, which is more niche. The P channel is like objectively a worse device from a physical perspective. It's just that the way the gate works, it's like convenient in some applications, but like nobody actually uses them in discrete circuits unless you're like really desperate. You would just use an N channel with a gate driver. So there's a few key parameters. Again, not going to dive into too much detail. The max voltage it can handle. The on-state resistance is important because it's like a switch, but when you close the switch, it's not not perfectly on. There's going to be some resistance. This is very, very low value. And then the gate charge, this is sort of related to what I was talking about. When you switch a MOSFET, you always lose a little bit of energy. And so how much energy you actually lose when you do that switch, this is what affects that. You can also drive it at different voltages. If you just provide like 3.3 volts, this MOSFET actually won't even turn on. So you sort of need to go all the way up to 5 volts. And then you do have some on-state resistance, but as you increase the gate voltage, you get a lower amount. And also it's temperature dependent, because you can see there's two curves here. The black one is for 25 Celsius and the red one is for 125 Celsius. So if you're making a converter, you do some math, it's going to heat up a little bit, but it's going to be okay. Well, actually, as it heats up, the resistance gets worse. And so then it'll heat up even more, and you can have a runaway. So there's a lot of factors to consider with MOSFETs. All of these like parameters that are really important, these end up really mattering a lot when you're doing switching converters. If you're just using a MOSFET to turn on and off like a motor, an LED or something like that, you generally don't have to worry about most of these, but they're good to know that they exist. Yeah, you'll probably cover MOSFETs in some of your courses, but this might be a second year thing. I'm not sure. But generally, it's a 3-terminal device. Input, output, and the control pin is the simplest way to explain it. These are they're kind of confusing. Gate obviously makes sense. And then you have drain and source. The drain, you connect to the positive side. Current flows from the drain to the source, which doesn't make sense like verbally. But it's because that's conventional current. Technically, current flows from the negative pin to the positive pin. So it's kind of confusing, but just look at a diagram if you need to. To turn it on, you basically need to generate a difference between the gate and the source pin. And so you can see on this little diagram down here, this is an LED being driven from an IC that actually, like we talked about earlier, it cannot generate a positive voltage. It cannot source current. It can only sink current. So the way this circuit works essentially is we have a 3.3 volts pulled high through a 100K, which means our IC, when there's no fault condition and everything is okay, this just floats, doesn't do anything. That means this MOSFET, the gate pin, gets pulled up to 3.3 volts, which opens the gate, and then current can flow from our power through the LED. LED turns on, it's good. But when there's a fault condition, it basically pulls this pin low. That's all it can do. It can't pull it high, but it pulls it low. Because 100K is a very weak amount, it will very easily pull low. That brings the gate to 0 volts, and then closes opens the circuit so the LED turns off, indicating there's a problem. So yeah, main uses for MOSFETs is switches. Like microcontrollers are literally just like millions of MOSFETs spammed together in a specific way. CPUs are also just billions of MOSFETs. So just to solve the issue, basically, of when MOSFETs are rated to turn on, they're rated for like a VGS, a voltage at the gate to the source threshold, which is fine in this case because the source is connected to ground, which means if you just generate 3.3 volts, you're good. It turns on. There you go. The problem is if you don't connect the source to ground, like right here is what's called high side switching, where you have like 24 volts and you just want to turn the 24 volts on or off, to allow them to go to the rest of the circuit, which is also taking 24 volts. The gate and the source are not at 0 volts. And so if you just try to apply 3.3 volts to the gate, nothing would happen because it's not above that voltage threshold. Really what you need 24 volts plus 3. So you really need 27 volts on that gate. You obviously cannot generate 27 volts using a microcontroller. So this is kind of an annoying situation. You try to kind of avoid it if you can, but if you do need to do high side switching, the solution is a gate driver, and a gate driver just does exactly that. It generates a voltage difference, usually at least 10 volts between the gate and the source, and you can control it using a regular 3.3 volt signal, which is very convenient, very good. I will say, like, if you can avoid it, definitely avoid doing this. Gate drivers are kind of expensive and stuff. So really what you do is you get a load switch, and a load switch is just an integrated circuit that has both of these things together in the same chip. Like a MOSFET and a high side gate driver. The challenge is that when you get to really high powers, like 20 amps plus, the load switches don't exist. You need to make your own. So this is just something to be aware of, that switching high voltage with a MOSFET, you might need a gate driver, and it's not going to just work if you just plug it in. That's pretty much, that's all to say there. So we're gonna sort of switch gears here to more a little bit about sort of what's out there and what we use in our systems. Just sort of broad overview. So attitude sensors are very important for just basically detecting where you are. Probably seen the meme, like the missile knows where it is because it knows where it isn't. That's kind of where that comes from. Yeah, I'm sort of, this is an excuse to put this in here. I think ring laser gyroscopes are super, super cool. Gyroscopes basically measure rotation rate. And the way ring laser gyroscopes work is basically by measuring like the diffraction of the light, like a super microscopic effect. And this is what real like ICBMs and fighter jets use. They all have ring laser gyroscopes in them. Yeah, but unfortunately we're stuck with these little chips here. They're okay. They're not as good. Yeah. So inertial measurement units, just another word for an integrated gyroscope and accelerometer. Magnetometer measures Earth's magnetic field, and you can detect your orientation that way if you know where you are. GPS position. GPS, obviously everybody knows what that does, but one thing you might not know is that it actually provides speed and altitude as well. And the barometer provides air pressure, altitude, obviously. These are all sensors that are on board our system. And if you work on any personal projects, you'll probably encounter using one of these at least once. So they're good to know about that they exist. Yeah, in terms of electrical sensors, obviously you have digital signals, which are either 0 or 1. And you can transmit more complex stuff using zeros and ones, like with SPI, I2C, those things. But ultimately, those are really just 0 or 1. If you need to read an analog signal, like either measuring the voltage on a power supply or the current going through a power supply, which are both things we do on the power management board, you need an analog to digital converter, also called an ADC. And it basically converts analog signals into bytes, and then you can read them over SPI or I2C to your microcontroller. So we use these on the peripheral boards, on the power management board. Most microcontrollers have a kind of like bad ADC built in that's like good enough. But if you're trying to measure like sensors for the propulsion system, you have a dedicated one, which is what we do. And just a side note on this, if you want to measure current going through some device, the correct way to do that is using a current sense resistor. So you have a really small resistor, like 1 milliohm, and then you run the power through it. And as you know, obviously resistors dissipate, resistors will have a voltage drop proportional to V equals IR. And so you know the resistance, and then you measure the voltage. Now the voltage coming off there, you obviously want to pick a small resistor, because if you pick a big resistor, you're just dissipating a bunch of heat from your power supply, which you don't want to. So you're going to have a very small signal. You basically use an amplifier, an op amp, which you will probably cover in courses, but it basically just significantly increases the amplitude of the signal. So if it previously was like 0 to 1 millivolt, crank it up 1,000 times, it'll now go 0 to 1 volt. Then you can read that using the ADC and just do the math on the resistance value. And that's the proper way to measure current. And those are both things we do in our system to monitor the power. So that's that. Brief overview of RF circuits. So we do have some RF circuits in our system. It is a huge topic, RF circuits. Generally, sort of above 100 megahertz is where you should start watching out for these sort of weird effects that happen. You just have to be very careful about how you route your PCBs, how you route your wires. You have to start using coaxial cables. You have to really care about interference, both receiving and generating interference. And the most important thing, just to keep in mind if you do work on any RF stuff, at least so you know what to look up and what to sort of pay attention to, is a concept called impedance matching. And impedance, think of it as resistance for now if you're not super sure what it is. Basically, all that this is about is every component, every wire, every trace on a PCB, every aspect of an RF system operating at a high frequency has a so-called characteristic impedance, which is, if you really squint at it funny, your professors are going to hate me for saying like this, but it's basically like how much of a resistor it looks like. And so the standard is that it looks kind of like a 50 ohm resistor at a high frequency. I know it's weird, but I'm happy to go into detail about the details of that after the presentation. If anyone's curious, we can chat afterwards. But the key thing here is if you have a component that is internally designed and impedance matched for say 25 ohms, and your PCB trace is 75 ohms, you're going to the best case scenario is you lose a little bit of power. It's a little bit less efficient. Your signal degrades a little bit. But the worst case scenario is that you end up having just complete loss of the signal integrity. You cannot discern from what it originally was because you get so much interference between the different frequencies, because you basically get reflections whenever there's a mismatch. So basically you want to make everything be 50 ohms. Part of this is mostly solved by buying components that say 50 ohms on them. And part of it is also solved by when you make a PCB, the traces need to be a very, very specific thickness depending on the distance to the layer below. And it's just something to be aware of if you're doing the RF stuff. Speaking of RF, another common topic within at least especially commercial product design, but also on avionics as well, is electromagnetic interference. We care obviously mostly about receiving interference. We don't really care about other people that much because our rocket is experimental and we're going to fly the system once, et cetera, et cetera. If you're designing like a laptop, EMC compliance is extremely important because you have to go through regulatory agencies like the FCC. They put you in a room like this and they test all the emissions coming off of your electronic system. And the main way this really happens is when you have like power or high-speed digital signals that are switching. If you're not careful about how you do the layout, they will end up acting like a small antenna and just radiating like random garbage. And so that's bad, if you're designing a device and you want to pass that test. But even if you're just for your own system, if you receive interference from other systems, or you have a power stage and then you have like a GPS receiver right next to it, you could potentially mess up your GPS receiver's sensitivity and performance just by having this switching converter nearby. So, this is just something that will come up. I'm not going to go into like exactly what causes it, today, but just it will come up in PCB review and layout and design and stuff like that. Especially important at the layout stage. So PCB stack-ups, now we're sort of tying it into what's going to be happening at the next workshop, which is going to be hands-on Ultium PCB design. Hopefully everybody can get your licenses and stuff installed. It'll be less of like, it probably won't even be in a room like this. Not going to be like somebody at the front. It'll probably be like a tutorial room or something like that. Everybody will have Ultium out. We'll work on it together. Probably take a bit longer for sure. But we'll take our time, go through making a PCB hands-on. And, at the end, it should be something that in principle you can manufacture if you want to for like probably 40, 50 bucks. It's actually cheaper than you think. With your name on it, with whatever components you place down. Talking about PCBs themselves, you look at them from the outside and it's pretty obvious, like, okay, it's a printed circuit board, sure. But it's good to understand just internally what's going on. Typically, the way they're manufactured is with a fiberglass core, fiberglass core, and then there's a couple different parts of it. So for 2-layer PCBs, they just bring them to the factory with a fiberglass sheet and then copper bonded on both sides already. And then you obviously have individual traces, but they just start with the copper fully. Oh, screen turned off. Okay. Start with the copper on both sides, and then they just use basically a drill bit, obviously on a CNC machine, to mill away where you don't want copper. Now, if you want to make a 4-layer PCB, it gets more complicated because obviously you can't reach inside and mill it out. You have to start with separate pieces and then bond them together. And that's where prepreg comes in. So prepreg is used for those external layers. Generally, there's a few sort of structures you need to be aware of within a PCB, and that is vias is the main one. Vias is how you get signals from one layer to another. And all it really is a hole that you've drilled and then plated with some sort of metal that is conductive, typically copper. And vias can be used to connect the top to the board to the bottom, but also internal layers as well. And you have traces, obviously. This is the main thing you need to know. In terms of doing like a digital layout, some small little test project, you probably don't need to worry about the physical spacing of these layers, like how thick is the core, how thick is the copper. Those aren't things you really need to worry about. Although you definitely should know like the layer count and sort of which ones are closer to each other. But really in RF and power, you end up caring a lot more about the stack up. And the reason is that thing I mentioned with getting like a 50 ohm impedance on your traces. That depends on the spacing to the layer below. And the only way you can know what that spacing is by going to your PCB manufacturer and figuring out what is the actual thickness of this prepreg they're going to use, and then you can design and calculate your trace accordingly. So we'll do more details on that during the actual workshop. Should I mention oscilloscopes? You'll probably cover this if you're in EC some of your classes, but if you're not in EC, you may not cover this. We do have an oscilloscope in my hall. We're hoping to get a better one now. Basically, what it does is it just measures voltages. It's like a really, really good ADC, and it's just dedicated for testing stuff. So just good to know. The interface can be kind of confusing. So hopefully, as we do some hands-on just work sessions, not like training workshops, but just as we're genuinely doing stuff for the rocket, we'll get some hands-on experience in an oscilloscope. But it's good to be aware of whenever you're not sure what's going on with your circuit. Generally, an oscilloscope is your sort of go-to to measure what's going on. Yeah, most oscilloscopes are not really good for RF. When you get into RF stuff, you have to use special tools because RF frequencies are the oscilloscopes that can measure RF are like hundreds of thousands of dollars. So you end up having to use like fun tricks to bring your frequency down to like a readable range. Yeah, quick overview, just assembly and stuff. I'm sure like everyone's kind of familiar with like how you solder regular stuff. I'm sure most people have soldered or at least seen it. The soldering iron. Assembling embedded systems, especially in Rocketry, is a little different because we have such small components that have very fine pitched leads on them. The way we do it is you get your bare PCB and you actually buy what's called a stencil, which is like a very thin stainless steel sheet with laser cut cutouts basically on each pad, and then you put solder paste on it and just squeegee it across, and then you individually pick and place the components. This is going to be something we're definitely going to be doing together if you guys do make it to the work sessions, is like picking and placing components on. And then once they're on there, you have the solder paste. Now solder paste, really all it is like a little bit of flux to like keep everything together, and very, very small solder balls, basically. And that's why it's a paste and not a solid thing like typical solder is. You can use a few different options to assemble it. Hot air gun is an option. I don't love it. The hot plate is my personal favorite. I have this exact one at home. Reflow ovens are great for pros if you have tens of thousands of dollars. Generally, you can get some smaller ones for like a few $100s, but it's like, yeah, mostly what the pros use. But these two, you can make any board with these pretty much. Yeah. So we're pretty much done now. But just to wrap up the stuff. So for the next workshop, get a student license for Altium Designer. Open it up. Make sure you can create a PCB project. Our current Altium license situation is kind of, you probably overheard me talking to some people about this earlier, but it's sort of up in the air. We definitely will be having it. It's just that, so I reached out to them because our workspace was locked, and then they said, okay, we can, what's your email? We can convert it to not that. We'll make you the workspace admin. I said, okay, so here's my email. And they said, okay, sure, but by the way, we're going to like completely delete your personal projects, and you're going to be like the workspace administrator only. Like, well, I have like 10 personal Altium projects. I mean, I've already made them, but I don't really want to delete all the files. So I'm sort of, we're going to have to figure out something about that. I think we're going to have to make a dedicated like Altium administrator email for the team. And so that's what we're currently waiting for that. Thankfully, this will not impact the workshop at all because you should make all the next PCBs on your own personal thing anyways, but it'll slow it down a little bit. Yeah, I hope that was pretty concise and but still useful. So we can have a little open discussion time. Come up, talk to me, or just ask questions from there. Or feel free to go home too if you want to. But yeah, hopefully this gives a good sort of background for what we're going to be doing for next year. Next week, it'll make more sense when we're talking about the different components. We're providing like an LED, LDO, current limiting resistor. Like you have an idea of these things now. Make more sense. But yeah, any questions or yeah, what's up on the right? Yeah.
Yeah, for buck boost conversion, you're decreasing the voltage. Do you have to worry about increasing the amount of
Yes, yeah, absolutely. So basically power has to always be maintained, obviously, because conservation of energy. So if you have like let's just say 20 volts in the input, 10 volts on the output, if you are drawing 2 amps on the output at 10 volts, you are only going to be pulling 1 amp on the input at 20 volts for 100% efficiency. So you're right, yeah. You can generate much higher or lower currents depending on the direction you're going in. Yeah. So, you can use KiCad with GitHub. Altium Designer is significantly superior. Yeah, I'm sorry. I'll give you some. Sure, we're still doing that. I'd love to. I'll give you. I'll show you some things to love about about the Ultium 365. So one thing is obviously you can leave comments in specific things, which you can't not do with KiCad nearly, or sorry, can't do with GitHub nearly as conveniently. So you have to like clone the repo all the time. I can always see live updates here. It has a web viewer for you to the PCB. The main thing is just Ultium Designer has a lot more features. Inductors, yeah, sure. I might close the. Oh, impedance, yeah, sure. Yeah, so impedance basically arises when you're looking at an electronic device that is like a resistor. You'll notice a certain amount of current flow through it based on whatever voltage amplitude you apply. When you have an inductor, if you apply a changing current, a changing voltage, you will see some current pass through that based on the inductance. And impedance is basically the equivalent extension of that. So what you end up having is not just a value for resistance, but also an amount of either inductance or capacitance. And that ends up being a position on the, I'm not sure, do you know about complex numbers? Have you roughly familiar with that? Yeah, no, it's all good. So, let's pull something up here. So yeah, you have a resistance amount. That's your x-axis, your x position. And then you have some y position, which changes with frequency, by the way. So we have j is just I. It's like the imaginary number constant, square root of 1. They sometimes just say it's j instead of I. Omega is the frequency. It's the frequency, which is, again, comes down to the fact that you have frequency-dependent effects with impedance times the inductance. And then this gives you your Z value, which is you can either state it as the absolute value of it, and just talk about how much impedance it is. But more correctly, you state how much of it is resistive, how much of it is inductive. In the exact same way with a capacitive system, you have some resistance, and the capacitance, it's a slightly different formula like this. Now, in terms of where that tie into RF stuff, when you look at what's called a transmission line. So a transmission line is like literally any wire, but like let's just think like a coax cable used to transmit TV, for example. Oh no. Okay. Here we go. Yeah, if you from a simple perspective, a coax connector or a wire is just instantly links up point A to point B, and there's nothing magic happening in between, and it's just like now these two are suddenly connected and we're good. But at high frequencies, you kind of have to that model basically breaks down, and really what's going on is that at each little incremental aspect of the line, like every millimeter, every infinitesimally small part of it, it is slightly a resistor because it's not perfect. It's slightly a capacitor because you have some distance between your ground and your power, and it is slightly an inductor because you have parallel current flow, and those come together. You have a characteristic inductance, resistance, and capacitance per unit length, and basically the ratio of those, that ends up forming some number of impedance, some value of impedance, and that is 50 ohms, for example, in a coax cable. Like they specifically designed so there's a lot of factors actually that affect coax cable, but you have whatever the insulation is, whatever the diameter of the metallic shield is, and whatever the diameter of the internal wire is. changing the ratios and changing those things will get you different impedances. Your per element inductor, capacitor, resistor values will be different. And yeah, and it's really what it looks like to a high frequency signal, which is kind of a weird way to explain it, but it doesn't make sense at DC. Obviously, if you just turn it on, it's like 10 volts is on there and it's flowing through like, I don't know, 1 amp. There's no impedance. Like, it's not, what do you mean there's no impedance? What does that even mean? It's really when you have a switching frequency, high frequency signal, that the impedance actually makes sense as something. Like next week, I mean, like the workshops are very, okay, I hope the workshops are like reasonably well structured and there's sort of the illusion that like we know what we're doing and like everything is, perfectly planned. From a tooling perspective, that is definitely true. But after next week, I hope everybody gets some hands-on experience with PCBs. It's basically going to be like, hey, here's an exhaustive list of projects we're currently working on, and pick one you're interested in and start working on it. Some of them will be more basic. Some of them will be more complicated. Some of them might be like R&D. Like you come up with something like, I think this would be useful for the team, for the rocket. And it's basically just you work on it during the week, reach out to us for support. During our weekly meetings or work sessions, we'll be chatting about it, and there'll be some in-person work sessions like assembling some PCBs that are already designed, but we're gonna have to get them manufactured. But it's not like the complexity of PCBs you design over the next week, it completely depends entirely on how motivated you are and what list of sort of tasks we end up generating by that point. Yeah, what's up? Yeah, definitely. So I would say after next week, we'll do the sort of Altium hands-on workshop. It'll be a basic PCB. And at that point, I would recommend, now that you've gotten some hands-on experience with the tools itself, I can recommend you some videos that walk through basically designing much more complex boards from scratch. But then at some point, really, it's just like you understand the tools, you understand the principles, you are motivated and going to spend time to ask us questions about it. It's just a matter of doing it. It's okay if you don't have experience. You sort of gain the experience as you do it. You don't have to come into it with like, oh, I definitely know how to do this, so I'm going to do it. It's kind of like, I'm willing to do this. It sounds interesting, and not like completely off the deep end, and sort of iterate on it. Yeah, that's true. I like Ben Eater. What's up, Eric?
I think I said it, but the ultra big 5 is broken right now. So
Yeah.